Greetings, this is Dr. McGuire, and this is the third screencast for Chapter 17, in which I focus on Section 17.3 with the following learning objectives. Define degrees of freedom for chi-square test for independence, and locate critical value for a specific alpha level in the chi-square distribution. So what we'll find is that the formula for degrees of freedom is different for this chi-square test, but locating the critical value, we use the same process as we did when we located the critical value for the chi-square goodness of fit test. 2. Describe the hypotheses for a chi-square test for independence and explain how the expected frequencies are obtained. And 3. Conduct a chi-square test for independence. Alright. The chi-square test for independence uses the frequency data from a sample to evaluate the relationship between two variables in the population. This is in contrast to the goodness of fit test, in which we were just looking at one variable with several categories, well, with at least two or more categories. Each individual in the sample is classified on both of the variables, creating a two-dimensional frequency distribution matrix. The frequency distribution for the sample is then used to test hypotheses about the corresponding frequency distribution in the population. So let's turn our attention to a practice problem that illustrates some of these points that I just made. And the practice problem is going to be problem number 13 at the end of the chapter, and we are on chapter 17, located on page 599. And let me increase the font here so we can see this better. So here is the problem. I'm going to go ahead and read the problem. Feel free to fast forward, pause, and read it on your own if you wish. In a classic study, Loftus and Palmer, 1974, investigated the relationship between memory for eyewitnesses and the questions they were asked. In the study, participants watched a film of an automobile accident and then were questioned about the accident. One group was asked how fast the cars were going when they smashed into each other. A second group was asked about the speed when the cars hit each other, and a third group was not asked any question about the speed of the cars. So at this point, we have three groups of participants, and we can say that they fall under one independent variable, which is how they were asked, or the verb that was used. Now let's continue on. A week later, the participants returned to answer additional questions about the accident, including whether they recalled seeing any broken glass. Although there was no broken glass in the film, several students claimed to remember seeing it. Alright, so here is our second independent variable, or our second variable that we're concerned with, is the number of people that claim to see glass when in fact there was no glass. By the way, this I have read this say this is a very fascinating study, and typically Loftus gets cited in studies where they are questioning eyewitness testimony. Anyway, so let's turn to the table of data. And this is going to be the table of data that we will use to illustrate how to conduct a chi-square test of independence. And so what we see here is the three groups in terms of what they were asked. So some people were asked how fast were the cars going when they smashed into each other, when they hit each other, and then a third group was not asked any questions. And then we have a follow-up question a week later. Did you see broken glass? And so 16 of those that were in the smashed into group said yes, whereas 34 said no. And then 7 in the hit group said yes, whereas 43 said no. And then 6 in the control group said yes, whereas 44 said no. Okay, so that's our data. Let's return back to our PowerPoint. The null hypothesis for the chi-square test for independence states that the two variables being measured are independent. That's at a general level. And this general hypothesis can be expressed in two different conceptual forms, each viewing the data and the test from slightly different perspectives. The first perspective is that the data are from a single sample with each individual measured on two variables. The null hypothesis states that there is no relationship between the two variables. This is very similar to what you would come up with if you were conducting a Pearson R. The second perspective is that the data are viewed as two or more separate samples representing two or more populations or treatment conditions. The goal of the chi-square test is to determine whether there are significant differences between, or in the case of three or more, among the populations. The null hypothesis states that there is no difference between or among the populations. So in our case, in our sample, we had smash, hit, and a control. We actually have three groups there. And we are looking at this being similar to what some might consider a one-way between groups analysis of variance. Two variables are independent when there is no consistent, predictable relationship between them. In this case, the frequency distribution for one variable is not related to or dependent on categories of the second variable. As a result, when two variables are independent, the frequency distribution from one variable will have the same shape or the same proportions for all categories of the second variable. The chi-square test for independence uses the same basic logic that was used for the goodness of fit test. First, a sample is selected and each individual is classified or categorized, and we saw that in the sample problem whenever I turned to the Excel file. Because the test for independence considers two variables, every individual is classified on both, and we saw a resulting frequency distribution. As before, the frequencies in the sample distribution are called observed frequencies and are identified by lowercase f subscript o. And then the next step is to find the expected frequencies. But before we do that, let's return back to our Excel file and look at our steps for hypothesis testing. The first step we see is to state the hypotheses. So let's do that real fast. Let's look at how we would go about stating the hypotheses. And I have that hopefully here. Yes, here we go. Okay, so there are two versions. The version that the problem is asking, and this I did not write up, or I did not have in Word, 13 part A is asking, does the proportion of participants who claim to remember broken glass differ significantly from group to group? And when we look at the description of the null hypotheses, that question in 13 part A really gets down to version 2. And so if we were to come up with a null hypothesis coming from that second perspective, we would say the following. The proportion of participants who falsely claim to remember broken glass is the same for each of the groups in terms of which verb is used to ask about speed of the collision. So this is very similar to a one-way ANOVA because ultimately we are looking at group 1 that received the verb smashed, group 2 that received the verb hit, and group 3 that did not receive any verb or did not receive a question about the collision. Therefore, the alternative hypothesis would be the proportion of participants who falsely claim to remember broken glass is different for each of the groups in terms of which verb is used to ask about speed of collision. All right, so that is our first step, and our second step is to determine the degrees of freedom and locate critical region. I want to turn our attention to the second step because the point at which I left off in the PowerPoint really is concerned with this step, step 3, determining expected frequencies. So how do we determine the degrees of freedom and locate the critical region? All right, to determine the degrees of freedom, we need to know how many rows there are and how many columns there are. And once we know our matrix, how our matrix is set up, we remove the last column and the bottom row from the matrix. So basically you are left with a smaller matrix that has C-1 columns and R-1 rows. The remaining number of cells that you have left in the smaller matrix determines the value for the degrees of freedom. Another way to calculate this, I mean, you can kind of visualize this, but another way to do this is just take R-1 times C-1. Okay, and I've done that already in our Excel file. If we look at how many rows we have 1, 2, 3. So rows minus 1 is going to equal 2. And how many columns do we have? 1, 2. 2 minus 1 is 1. So over here in step 2, I have gone ahead and calculated our degrees of freedom, which you can do in your head, but I went ahead and wrote it out so you can see conceptually how it was calculated. The problem, if we look at, again, the problem part A of 13, we're setting alpha equal to 0.05. So now, like in the last type of chi-square test, goodness of fit, we just turn our attention to the table of critical values, the chi-square distribution, and we look for degrees of freedom equal to 2, and then the column where alpha is set to 0.05, and what you'll find is a critical value of 5.99. Now the third step is to figure out the expected frequencies and compute the chi-square statistic. Okay, so when we do the expected frequency, well, to calculate the chi-square, we need to figure out what our expected frequencies are. And as before, the expected frequencies define an ideal hypothetical distribution that is in perfect agreement with the null hypothesis. Once the expected frequencies are obtained, we compute the chi-square statistic to determine how well the data fit the null hypothesis. Our attention back to the Excel file and then figure out how do you calculate the expected value. So up here in this portion of the spreadsheet, I have the observed values. This is our sample data. And as you can see, I've gone ahead and calculated the column totals and the row totals. This value here is the sample size. We have 150 participants in the study. And I've just copied the row totals and column totals down here. Now we got to figure out what the expected frequencies, what value goes into there. Well, there is a formula to use in each of these cells, but I want to review the logic behind the formula that is discussed in the text. So one way to think about this is there is a proportion of people that will say yes, or that said yes, in the response about broken glass. Okay, so how do we figure out that proportion for this cell? Well, what we have to do is calculate, well, how many said yes? All right, so 29 people out of 150 said yes. Well, what is 29 divided by 150? And I have that value here. And what I did, well, you can see up here in the formula, I just took 29, which I have here, divided it by the total number, and that gives me a percentage of how many people said yes. And that percentage is, or that proportion is 0.19333. Okay, so now what I need to do is take that value and multiply it by 50. So, and when you do that, you get, oops, you get 9.666667, or 9.6 repeating. Now, why did I take this percentage or this proportion and multiply it by 50? Well, because I know that 19% of the total population, or of the sample, said yes. And so now I need to take that proportion and multiply it by the number of people that were in the smashed into group. Hopefully that makes some sense. If not, let me know and I can elaborate more. But there is an easier way to figure out the expected frequencies for each of these cells. And that is simply to use the following formula. You take the frequency of the column, which I have down here, times the frequency of the row, which I have there, divided by the sample size, which I have right there. And so 9.6 repeating is our value, our expected value for yes responses in the smashed into group. Now, one of the things that's interesting here is that this value 29 is going to stay the same for this and this, and 50 is going to stay the same as well. So we'll get the same values here and here. And given that this does repeat, it's best to make sure that when you actually do the division, so I'm sorry, the operations, the mathematical operations, I'm taking C15 times the row total for hit divided by my sample size. And so I'm going to repeat this again for this cell, and then I do the same process for this column of data, but in this case I'm taking 121 times 50 divided by 150. Okay, and I just repeat that. Okay, so I'm going to repeat the same process here, but before I do, let's just copy and paste this formula. Now D15 is going to stay. I want to keep on referencing D15. E12 can vary, so we can go E12, E13, E14, and E15 is going to stay the same. So I'm going to press F4 to make that an absolute reference. So now I can copy and paste and get these values. Okay, so now I have my expected values. What do I do next? Well, let's turn our attention to the formula for chi-square. It's the same as the formula for when we conducted the goodness of fit test. We need to take the frequency observed minus frequency expected for a given cell in our matrix. We square that and divide it. After we square it, we divide it by the frequency expected again. And then we add up all of these together to get our chi-square. So we sum up all of these deviation scores squared that have been divided by the expected frequency. So let's do that next. And what I have here are the frequency observed minus frequency expected, or a column that's devoted to that. So I'm going to say this is equal to frequency observed 16 minus frequency expected 9.6 repeating. And I can go ahead and copy this down for the first three values because I'm looking at these three, and when I drag down, it drags down with these three. Okay, so now I'm going to do the same thing, but I'm going to look at these values. So there's the frequency observed, a minus frequency expected, and then I'm going to drag this down 3 times to capture frequency observed, frequency expected, frequency observed, frequency expected, and so forth. All right, so now I have all of my deviation scores, and now I need to take those deviation scores and square them, which I've done in this column. And again, what I did was, if we look at the formula, I just referenced the frequency observed minus frequency expected and took it to the second power, and then copied that in these cells. The next thing I did was I took these squared deviation scores and divided them by the appropriate expected frequency value. So for example, I took this value 40.111 and divided it by the value in C12, which in this case is 9.667, because this is the expected frequency. The next thing I did was I created a sum cell where I just summed up all of these scores. So this is our chi-square. Now we just need to go to step 4 and make a decision about the null hypothesis and the outcome of the study. And so we have one of two decisions to make. If our obtained test value is less than the critical value, then we fail to reject the null hypothesis. If our obtained test value is greater than the critical value, then we reject the null hypothesis. And this, in fact, is greater than our critical value. So we would reject the null hypothesis. And if we go back to how we stated it, the proportion of participants who falsely claim to remember broken glass is the same for each of the groups in terms of which verb is used to ask about the speed. In this case, this is the null hypothesis. We would basically state our findings in terms of the alternative hypothesis, in which case we would state something like the proportion of participants who falsely claim to remember broken glass is different for each of the groups in terms of which verb is used to ask about speed of collision. All right, and now we've gone through the hypothesis testing. How would you go about doing this in SPSS? To run this analysis in SPSS, I first need to create 3 variables. So I'm going to go to my variable view, and I'm going to name my first variable rows. But what rows represents is actually what one might construe as the independent variable, and that is the verb used to ask about speed. And in this case, we had 3 levels of this variable. The first level was being asked the speed of the collision when cars smashed into each other. The second level would be when people were asked the speed when the cars hit each other. And then the third level is the control condition. All right, so I have those 3 levels, and now I need to specify the nature of the scale of measurement, which in this case is nominal. Now I'm going to turn to the columns, and in this case, this was the response that participants provided. Yes, they thought there was glass, or no, there was not. And so for my values, I come over here, and my first value I'll say is yes, and then my second value I'll say is no. And then I'll go ahead and change this to the nominal scale of measurement. And then finally, I am going to create a third column, or third variable called frequencies. And in this case, I don't need to add a label, I don't need to add values. I do need to indicate the nature of the measurement, and frequencies is nominal. All right, so now I just have to enter in my data, and for each level of the independent variable, there are 2 categories. So I'm going to, whenever I put down my levels of the independent variable, yes, okay, so when I put down smashed, I need to make sure that I have a yes for my other variable, but note that not only do I have values in the smashed yes, but I have values in the smashed no. So I need to make sure that I get that recorded in here as well. So for each level of my variable, my rows variable, I need to have 2. Whoops, that should be a value of 2. So I need to have 2 instances of hit, and then I need to have 2 instances of control, because for each instance I have a yes and then I have a no category. So I simply go 1 2 1 2 1 2 1 1 2 2 and 3 3 for my rows. Now for my frequencies, I just go ahead and put in what my frequencies were for this. So for the smashed yes, I had 16. For the smashed no, I had 34. For the hit yes, I had 7. For the hit no, I had 43. For the control yes, I had 6. And for the control no, I had 44. Okay, now given that I've entered the frequencies for each of these combinations, I need to let SPSS know what I've done by indicating that I want to weight the cases. So I need to weight cases by frequencies. All right. Now I'm going to get an output table, which I don't need to look at yet because I want to run the analysis. Now there's a big difference between running goodness of fit and test for independence. The test for independence, in both cases we go to analyze, but for the test for independence we need to go to crosstabs because it is a cross tabulation. And once we get to cross tabulation, now I need to enter my variables in the right boxes, and that's one of the reasons why I used rows and columns, so I knew where to enter those. And then I have to indicate, so I just put my variables, and then I need to indicate which statistic I want to calculate. In this case, I want to calculate the chi-square. Now it doesn't say test for independence, but that's what this is. The other thing we can do is look at bar charts, and we can look at tables of information that will give us our expected and observed frequencies. So let's do that next by clicking that check. Leave that unchecked and click OK. And here we go. So the first box is just case processing summary. How many cases did we have? 150. So that lines up with what we calculated. And then this tells us our actual values, our observed frequency counts, as well as our expected frequencies. And we can compare that to what we calculated and we'll get the same thing. And then the most important thing here is our chi-square value. So we found a chi-square of, what was it, 7.7799943, which when we round up is 7.78. We have degrees of freedom equal to 2. And we see that the significance value associated with this chi-square is 0.020. So if we were writing up our results, we would put in there p equals 0.02, which is less than a p-value of 0.05, so it is statistically significant. Okay, so that is how you conduct SPSS. That is how you conduct chi-square test for independence in SPSS. And so we've done it manually in Excel as well as in SPSS. So that's it for this screencast. Until next time, have a good one.